This video is a step-by-step analysis guide for doing a multivariate ANOVA or a MANOVA. So the data is the same as what we called in the lecture. If you look at the data view, you can see we've got our experimental condition in which people are either a Coldplay fan or a Neil Young fan, proper person or an idiot. And then we've got our four dependent variables: IQ, working memory, emotional intelligence and mental stability. And in this experiment we're interested in whether there's a significant difference between Coldplay fans and Neil Young fans in IQ, working memory, emotional intelligence and in mental stability. So why don't we just do 4 independent samples t-tests? Well, the reason for this is relatively straightforward. Simply, we don't want to check multiple p-values. So if we did the effective condition on IQ, we look at p-value for that, and then we do condition on working memory and we look at a p-value for that, condition on emotional intelligence, p-value, and condition on mental stability. That means we're checking 4 p-values. So we're checking a probability of something being less than 0.05 4 times. So we're just more likely to get false positive. Our indicative p becomes 0.2, which is 0.5 plus 0.5 plus 0.5 plus 0.5. So you've got a 1 in 5 chance of having a significant result through chance if we were to do these separately. So instead, what we do is run a MANOVA. This MANOVA is going to tell us if a condition has an overall effect on these variables taken together, and if it does, this gives us justification for looking at the simple comparison between condition on IQ, working memory, emotional intelligence and mental stability separately. So running a multivariate ANOVA is a relatively straightforward procedure. As usual, we go to Analyze, General Linear Model, and then we go to Multivariate. You click on this, and as you can see, it's got our experimental condition, Coldplay fan or Neil Young fan, our dependent variables, IQ, working memory, emotional intelligence, and mental stability. We've got our dependent variables list here, so we simply select all of these, and we put them into our dependent variable window. Then fixed factors simply are independent variables. So we put that in here. We're not doing a MANOVA, we haven't got a covariance, so you don't need to add that. We don't need to look at this either. So it's relatively straightforward. There are a few other things that we can ask for. If we go to options, we can ask descriptive statistics and estimate of effect size, so we can report our descriptive statistics table in detail. This will also tell us where significant differences lie, what's causing the differences. Estimate of effect size can be asked for as well. This will give us our partial S squared. Homogeneity test can be asked for as well. Now, we don't really need to display means for condition because we're already going to get the means for condition anyway, and we don't need to compare main effects. The reason we don't need to compare main effects is because if we get an overall effect of our experimental condition on our dependent variables, and then we look at our individual ANOVAs for the effective condition on IQ, effective condition on working memory, we don't need to do any post hoc tests for that, because if the ANOVA says there's a significant difference in IQ between Coldplay fans and Neil Young fans, then we know they are statistically significantly different. A post hoc test will give us identical information, it will give us the same p-value, nothing will change at all. So there's no point asking for that, it's completely redundant. So instead, we can leave that blank for now. And we can click continue. See, another thing that's not very useful is plots. I'm actually going to ask for plots just to show you and explain why they're not very useful. So we put condition on the horizontal axis, we click add and click continue. Okay, and that's all we need to do to set up this simple MANOVA. We click OK, and here's the MANOVA output. First thing you'll see is it says what your between subject factor is, condition, number 1 Coldplay fan, 2 Neil Young fans, and 50 people in each group. Here comes our descriptive statistics table. It's a relatively straightforward table. We've just got our mean and standard deviation for IQ for the Coldplay fans and for the Neil Young fans. We've got the same for working memory, Coldplay fan, Neil Young fan, emotional intelligence and mental stability. We also get total score. So this is the mean IQ of the sample, regardless of whether they're a Coldplay fan or Neil Young fan. Mean working memory score, regardless of whether they're a Coldplay fan or Neil Young fan, and so on. And we'd report these descriptive statistics accordingly in a nice, neat APA formatted table. So this is going to be a useful table, and we're going to come back to look at this later if we do find some significant effects within our ANOVA. Next thing we want to look at though is Box's test for equality of covariance matrices. Now if you remember, this is just an assumption check, and we want assumption checks to be non-significant. However, Box's test is incredibly conservative, so what actually matters in this, we want the p-value to be greater than 0.000. So if this was all zeros here, 0.000, this would be a problem. We'd have violated that assumption. But in this case, as you can see, we're nowhere near violating that assumption. It's not a problem whatsoever, so we know we can trust this subsequent table. There are ways of dealing with violations of assumptions and so on. So the multivariate test table is our first really important table. This is telling us here, this condition here is telling us whether there is a significant main effect of condition. Is condition affecting our 4 dependent variables in some way? It's not going to tell us which conditions are which dependent variables are affected by the experimental condition in any way. It's just saying, do we have an overall effect? And this is basically what you're looking at, is for statistical justification to look at further comparisons in your data. If this is non-significant, you stop here. You have no justification for looking any further. You'll see here that we've got all these different measures: Pillai's trace, Wilkes's lambda, Hotelling's trace, and Roy's largest root. When it's an effect, when we're looking at the effect of a 2-level independent variable, so in this case we've only got 2 groups, Coldplay fans versus Neil Young fans, it doesn't matter which of these statistics you take. As you can see, the f values, the df, the p's, and the partial letter squares are identical for them all anyway. It doesn't matter which one you look at whatsoever. So from looking at this, what we can see is experimental condition does indeed have a significant main effect on our dependent variables in some way, and we just write this up accordingly. So we write this up, and the reader can see this. We've got an effect, so they know what we're doing next is statistically justifiable. We write this up, and then we move on to our next stage, because all very well we know there's a significant effect of condition on our dependent variables when we're taking them together, but some may be affected and some may not be. They all may be affected, 1 maybe, 2 maybe, or 3 maybe. We just don't know, so we need to look at this in more detail. So the first thing we need to check is Levine's test of equality of error variances. This is basically saying, do we meet homogeneity of variance for the dependent variable that's IQ, the dependent variable that's work and memory, for emotional intelligence, and for mental stability. So we're checking this assumption for every single dependent variable. As you can see in this example, we have homogeneity of variance for all 4 things. So we know we're going to get pretty robust findings from this. So you can move on here, and then we look at our rather complicated test of between subjects effects table. So what can we see here? Well, this is the bit we want to look at. This is telling us what the effect of condition is on each of the variables separate. And we know we can do this because our previous multivariate test table said there's some effect of condition on these variables, so we can look at each one separately. So let's look at the main effect of condition on IQ, and as you can see, we've got a statistically significant effect with a big effect size. Likewise, we also see a significant effect on work and memory, and again we've got a decent effect size here as well, highly significant effect. And for the second 2, emotional intelligence, there's no significant effect, so there's no difference between our Coldplay fans and Neil Young fans in emotional intelligence, and nor is there a significant difference in terms of mental stability. So we just write this up accordingly. So what we also need to think about is, okay, we've shown as effective condition on IQ, but in what way? Which of the 2 groups has a greater IQ? There's a significant difference in these 2 conditions. We don't need a post hoc test because we know those 2 conditions differ. So what we need to know is just work out what direction it is. So let's just take IQ as the example. These 2 groups differ, so how do they differ? To find out, you can just look at Descriptive Statistics table on IQ. And say Coldplay fans have a mean IQ of 104.66. Neil Young fans have a mean IQ of 110.9. So from this table, we know that this statistically significant effect of condition on IQ is caused by Neil Young fans having significantly higher IQs than Coldplay fans. So we need to write up all these statistics accordingly make it clear to the reader where differences lie, what's causing them, and which conditions don't significantly differ from each other. Now, I did ask for plots for this, and you can see why plots are problematic. So, as you can see, Coldplay fan versus Neil Young fan, looks like a very large effect there. Coldplay fan versus Neil Young fan, looks like a very large effect, and you probably expect a large effect because we know these first two are statistically significant. There's a significant difference in condition for IQ and working memory, and these two figures do indeed look like there's a big difference. We also know that these two do not differ, but if we look at the graphs, they show an identical size effect in the opposite direction for this one. Well, this is a fundamental problem with when you look at these graphs. This is because there's no sorts of scaling on them at all. So it always produces a line that looks like a big difference no matter what. So in the case of working memory is 36.5 mean compared to around 41. And this one, for emotional intelligence, you can see it's 33 all the way up to about 34.75. So this tiny difference is huge. It's a relatively big difference. It's also huge. It just scales it to look like a large effect at all times. If this was 33.01 and the Neil Young fans had a score of 33.02, it just scale the axis different and produce a line that looks like that. So these aren't very useful. If they had error bars on them, they would be a little bit more useful. You'd see that the error bars, for example, for emotional intelligence would probably overlap, whereas they wouldn't for working memory. But as is, they're not the most useful thing for gauging whether things are different from each other at all. So it's a relatively straightforward process to produce this ANOVA. However, there is more steps that we'd have to look at if we had a more complicated independent variable, and that's what we'll look at in the next portion of the video. So this is the slightly more complicated data set now, which we've added another level to our experimental condition. And as you can see, basically it's all the same DVs, IQ, working memory, emotional intelligence and mental stability, but we've now added a third group. So we've now got Coldplay fans, Neil Young fans and now G.G. Allen fans. So we've now got a slightly more complicated thing, and this does necessitate a little bit more testing than in the previous example. So to set this up, we follow exactly the same process as before: general linear model, multivariate ANOVA. Condition being our fixed factor, and then we've got our dependent variables. Now there's some stuff we should really look at. You can ask for descriptive statistics, estimates of effect size before, and homogeneity tests. So all those are standard. We can click continue, or we can ask it to do post hoc tests for condition as well. So you see it gives us loads of different options. The only ones we really need to think about is least significant difference test and the bond for only one, or if we violate the assumption of equality of variances for each of those individual ANOVAs, then we can use Tam-Haines T2. As is for now, what we'll do is we'll just look at post hoc test for condition, and we'll just ask for a least significant difference test, so we won't do any correction on p-values. So that, and then we can ask for plots. The plots make more sense than if you watch the bit with the 2-level independent variable. I showed you why they weren't much use, but they can be a little bit more informative when we have 3 levels. Okay, so it's all neatly set up. We've asked for a post hoc test this time round, and now we click OK. And this gives us our output. I'm not going to go into too much detail because we've already covered one of these already, but you can see we've now got our 3 groups, just an additional one, G.G. Allen fans, 50 people in that. Descriptive statistics table, just like before, because at this time we've got G.G. Allen fans up here as well, and of course this overall mean score is taken into account the G.G. Allen fans here. So relatively straightforward, no difference from before there. So we need to check if our boxes test the quality of covariance matrices, and we can see we've met this assumption because this number is bigger than 0.000, so therefore we have a quality of our covariance matrices. Now things get a little bit different here. As you can see, we've got a multivariate test table. Before, all these f values were the same, the degrees of freedom are the same, p-values and partial letter squares were all the same. But now, because our independent variable has 3 levels to it, you'll see everything's slightly different. even the degrees of freedom are changing, and partial letter squared. So there's these different ways of looking at the overall effect of condition on our dependent variables as a group. So generally speaking, currently at this level what we're looking at, we'll be looking at Pillai's trace or Roy's largest root. The general idea behind it, and the way you can think about this, if you expect one of your conditions to be very different from all the other conditions on your variables, then you'd look at Roy's largest root and you'd take that statistic. You'd write up Roy's largest root equals 0.59, and then you'd report the F value as degrees of freedom, partial letter squared, and so on. In this example though, we actually don't expect groups to be massively different from each other on everything. So we expect there's going to be some differences maybe, but we don't expect one group's going to be significantly low on all these things. So we don't expect one group to be really low on IQ, low on working memory, low on emotional intelligence, and low on mental stability compared to the other ones. So in this case, what we'll do instead, we'll report Pillai's trace. So this is very commonly reported when you do see multivariate ANOVAs being written up. So in this case, we're going to write up using this, and as before, you can see we've got a statistically significant effect of condition on our dependent variables. So this is just giving us a broad overview that somehow experimental condition, this 3-level independent variable, is influencing these 4 variables in some way. And again, it doesn't mean that the independent variable is going to affect IQ, and it's going to affect working memory and emotional intelligence and mental stability. It means there's some sort of effect going on in the data. It could be only IQ is influenced. It could be that IQ and working memory or any combination are influenced, and we don't know until we look at our ANOVA in a little bit more detail. So we write this up, report Pillai's trace and so on, and now the reader knows we've got justification for looking at the rest of things. So next thing we want to look at is Levine's test for equality of error variances. As you can see, in each case here, this is non-significant, and we want Levine's to be non-significant. If Levine's is non-significant, that means we've met the assumption of equality of error variances. If this did turn out to be statistically significant, when we do our post-hoc tests, instead of doing the least significant difference test, which I'm going to cover in a moment, what we'd actually look at would be Tam-Haines T2. So you probably want to rerun it, but just ask for Tam-Haines T2 as the post-hoc test, and then you can be a bit more confident in your post-hoc tests. But as you can see in this example, we've met this assumption, so it's positive. We can move on to the next table. So our multivariate table here has given us justification to look at the effect of condition on each thing separately. So what's this showing us? So the effect of condition on IQ is statistically significant, again large effect size. Effect of condition on working memory, statistically significant. Effect of condition on emotional intelligence, non-significant. And the effect of condition on mental stability is also statistically significant. Now, unlike when we did this example with the 2-level IB, we don't know what's causing these effects anymore. So we know condition affects IQ in some way, and our previous example showed that Neil Young fans and Coldplay fans significantly differed, so they're going to significantly differ again now. But we don't know where G.G. Allen fans fall into that anymore. There's no differences, we can't understand where these differences lie. So we don't know if Coldplay fans more or less intelligent than G.G. Allen fans, and Neil Young fans more or less intelligent than G.G. Allen fans, and so on. We'd need to do post-hoc tests. Likewise, condition on working memory, again we need to do post-hoc tests to look at this. Condition on emotional intelligence, this is non-significant, so we don't do post-hoc tests. We don't have a statistical justification to look at this in any more detail, so you write this up, but you do no post-hoc tests for it. And again, mental stability, of course, we do get a significant effect here, so again we need to do post-hoc tests for that. So all in all, we need to write up all these, do appropriate post-hoc tests where they're applicable, so for IQ, working memory and mental stability. So let's take, for example, IQ. There's a significant effect of condition on IQ. So what are the post-hoc tests telling us? Well, dependent variables, IQ, and these are all the comparisons. Remember, it does everything twice. So Coldplay fan versus G.G. Allen fan is the same thing as G.G. Allen fan versus Coldplay fan. So we only have to look at this comparison, and this comparison here. So what's causing this effect? So the ANOVA said IQ is in some way influenced by our independent variable, and as we look into this we can see This is because Coldplay fans, compared to Neil Young fans, have a significantly different IQ. Coldplay fans, compared to G.G. Allen fans, have a significantly different IQ. Neil Young fans, compared to G.G. Allen fans, no significant differences in IQ. So, if you want to know what's causing that, again, just like before, we need to look at our descriptive statistics, and let's look at the IQ. Coldplay fans' IQ, 104. Neil Young fans, 110. G.G. Allen fans, 110. So we know that the Coldplay fans have significantly lower IQs than Neil Young fans and G.G. Allen fans. Coldplay fans and Neil Young fans significantly different. We know their IQs are lower. Coldplay fans, G.G. Allen fans significantly different, and again we know their IQ is lower than their IQ. Neil Young fans and G.G. Allen fans don't differ. And we'd write this up accordingly and we'd give it the clear explanations. So if we move on to the next one, significant effect of condition on working memory. So what causes that? So let's look at working memory. Coldplay fan versus Neil Young fan, significantly different. Coldplay fan versus G.G. Allen fan, significantly different. Neil Young fan versus G.G. Allen fan, no significant differences. Again, what caused that? Well, let's look at the working memory scores. Coldplay fans' scores are lower than Neil Young fans and G.G. Allen fans. So we can write up an explanation of this part as well, quite neatly. Now, condition for emotional intelligence, we don't look at the post-hoc tests because we don't get a significant effect here, so we've got no justification for doing so. And if you glance at them, you wouldn't write them up, but you can see there's no differences there at all. If there was some significant differences, it'd probably be showing up in the ANOVA. So, final thing, condition has a significant effect on mental stability. So what's caused that? Coldplay fans versus Neil Young fans do not differ. Coldplay fans versus G.G. Allen fans do differ. Neil Young fans versus G.G. Allen fans do differ. Okay, so something's going on here. So Coldplay fans and Neil Young fans are no difference on mental stability, but G.G. Allen fans seem to be significantly different than both. So we look at our table, descriptives, what's happened. Mental stability scores for G.G. Allen fans are lower than they are for the Coldplay fans and the Neil Young fans. So again, we'd report and write this up accordingly here. So we've broken things down, we've got statistical justification for every step of the process that we've done. Just a quick look at profile plots, so you can see how it's a little bit more useful now. Coldplay fans versus Neil Young fans and G.G. Allen fans, you can see relatively similar for IQ, drop off there for the Coldplay fans. Similar process for working memory. Now emotional intelligence. Remember, this wasn't significantly different, but it does look like big effects still appear in this, so you need to be really careful still about it, but you can see it's still a better visualization of data than it was for the 2 level independent variable. And then we can see the mental stability drop-offs there for the G.G. Allen fans, much lower than the other 2. But again, you know, you could use line graphs to do this, but again, you'd really want to be including the error bars as well.